Hello students, welcome back to Sleepy Series. Tonight, we slowly revise. Shear in RCC, bond between steel and concrete, development length, anchorage and torsion. Relax your mind, no pressure, no panic, just calm revision. Listen slowly and let the concepts settle naturally into memory. The most important code for RCC design is IS 456-2000 for earthquake-resistant structures. Important code is IS 1893 for ductile detailing. Important code is IS 13920 for loading on buildings. Important code is IS 875. Now, before starting, a very short revision of limit state method. Limit state means the condition beyond which structure no longer satisfies safety or serviceability requirements. Mainly two limit states are considered: limit state of collapse and limit state of serviceability. Partial safety factor for concrete is 1.5. Partial safety factor for steel is 1.15. Maximum bending compressive strain in concrete equals 0.0035. Design stress in steel approximately equals 0.87 FAI. Now, we move toward actual behavior of RCC members. When beam carries load, internal stresses develop. Inside beam, upper portion of beam usually undergoes compression, lower portion undergoes tension. Between compression zone and tension zone, there exists neutral axis. Above neutral axis, concrete experiences compression. Below neutral axis, tension develops, which is mainly resisted by steel. If tension steel yields first, before concrete crushes, section becomes under-reinforced. Under-reinforced section is preferred in design because failure becomes ductile and warning is available before collapse. Balanced section means steel and concrete reach limiting conditions simultaneously, but practical design generally prefers under-reinforced behavior. Now, singly reinforced beam. Singly reinforced beam contains steel, only in tension zone. When moment becomes very high or beam depth becomes restricted, singly reinforced section may become insufficient. Then, doubly reinforced beam is used. Limiting moment of resistance is maximum moment resisted safely by singly reinforced section. If applied moment exceeds this value, doubly reinforced beam becomes necessary. Doubly reinforced beam contains steel, both in tension zone and compression zone. Compression reinforcement increases moment carrying capacity, improves ductility, and reduces long-term deflection. These beams are useful when depth restriction exists or moment reversal occurs. Now, flanged beams. When slab and beam are cast together, they behave as one unit. This forms T-beam or L-beam. In T-beam, slab acts as flange and beam acts as web. Compression zone extends into slab, which increases moment resistance. T-beams are economical because slab participates in compression. L-beam usually occurs at edge beams, where slab exists only on one side. Resultant compressive force in concrete equals 0.36 FCKB/XU. Line of action acts at 0.42 XU from top fiber for Fe 415 steel. Limiting neutral axis ratio approximately equals 0.48. For Fe 250, it is 0.53. For Fe 500, it is 0.46. Now, shear in RCC. When beam carries load, shear force develops inside beam. Shear force tries to slide one portion of beam relative to another. Nominal shear stress formula is tau V equals V divided by BD, where V is shear force, B is beam width, and D is effective depth. Maximum shear stress generally occurs near neutral axis. If shear stress becomes excessive, diagonal cracks develop inside beam. These cracks are called diagonal tension cracks. Diagonal tension cracks usually develop near supports, where shear force becomes high. Shear failure is dangerous because it occurs suddenly, without significant warning. Flexural failure usually gives warning through deflection and cracking, but shear failure can become brittle and sudden. Therefore, proper shear reinforcement is extremely important. According to IS 456, minimum shear reinforcement must always be provided, even when nominal shear stress is low. Now, types of shear reinforcement. Mainly three types: vertical stirrups, inclined stirrups, and bent-up bars. Vertical stirrups are most commonly used because they are simple, economical, and easy to construct. Inclined stirrups provide better resistance, but construction becomes difficult. Bent-up bars are longitudinal bars, bent upward to resist shear. Closed stirrups hold longitudinal bars together and improve confinement. Closer stirrup spacing increases shear resistance. According to IS code, maximum spacing of vertical stirrups should not exceed 0.75 D or 300 mm, whichever is less. Now, bond stress. Bond stress develops between steel and concrete to prevent slipping. Without proper bond, load transfer becomes unsafe. Bond allows steel and concrete to behave together as one composite material. Deformed bars improve bond because ribs create mechanical interlocking. If bond becomes weak, bars may slip and cracks may widen. Now, development length. Development length means minimum length of bar required to develop full stress safely inside concrete. Important formula: LD equals phi sigma S divided by 4 tau BD, where phi is diameter of bar, sigma S is stress in steel, and tau BD is design bond stress. Higher bond stress reduces development length. Larger diameter bars require greater development length. Development length is extremely important near supports, beam column junctions, and curtailment zones. If sufficient development length is not provided, bars may pull out before reaching full strength. Development length in tension is greater than development length in compression. Anchorage means arrangement provided to transfer force safely between reinforcement and concrete. Hooks, bends, and end anchorages increase anchorage capacity. Now, lap splice. When one reinforcement bar is continued using another bar, overlapping is provided. This overlap length is called lap length. Lap length depends upon development length, bar diameter, and stress condition. Lap splices should preferably be staggered to avoid weakness at one section. Now, curtailment of bars. Extra reinforcement may be terminated where bend in moment reduces, but proper anchorage and development length must always be maintained. Now, torsion. Torsion means twisting action in beam. Torsion develops when loading becomes eccentric. Torsional cracks usually form spiral pattern around member. Equivalent shear force formula is VE equals V plus 1.6 T divided by B, where T is torsional moment and B is beam width. Equivalent bending moment is also considered during torsional design. Closed stirrups are very important for torsion resistance. Longitudinal reinforcement also resists torsional stresses. Corners of beam experience high torsional stresses, therefore proper reinforcement becomes necessary. Combined effect of bending, shear, and torsion must always be considered during RCC design. Now, important rapid revision. IS 456 is main RCC design code. IS 13920 is important for ductile detailing. Under reinforced section is preferred because failure is ductile. T-beam consists of flange and web. Nominal shear stress, tau V equals V divided by BD. Diagonal tension cracks develop near supports. Vertical stirrups are most commonly used. Bond prevents slipping between steel and concrete. Development length LD equals phi sigma S divided by 4 tau BD. Hooks and bends improve anchorage. Torsion means twisting action in beam. Closed stirrups resist torsion. Shear failure is sudden and brittle. Therefore, shear reinforcement is extremely important. Good night, students. Relax your mind and let the concepts revise automatically. Sleep peacefully.